Welcome to D-Explainer. Today, we are going to tackle a classic programming challenge. How do you find every single subsequence that's hiding inside an array? We're going to break down a really powerful recursive pattern that basically unlocks the whole thing. So let's just start with a puzzle. You've got an array, something simple like 3, 1, 2. It looks straightforward, but there are a bunch of hidden sequences inside it. The real question is, how can you be absolutely sure that you find all of them without missing a single one? That's what we're going to build a mental model for today. Okay, first things first. Before we can start finding them, we need to be crystal clear on what we're even looking for. What exactly is a subsequence? So a subsequence is what you get when you pick elements from an array. The one crucial rule, the most important part, is that you have to keep them in their original order. You can skip elements, sure, but you can't just reorder them however you want. And this is the key difference that sometimes trips people up, especially when we talk about subarrays. See, a subarray has to be a continuous, unbroken block of elements. But a subsequence can have gaps. Like, you can take the 3 and the 2 from our array 3, 1, 2. That's a valid subsequence, but it is not a subarray because we skipped right over the 1. So, for our simple little 3-element array, it turns out there are 8 possible subsequences. You got the single elements, you've got combinations like 3, 2, you've got the whole array itself, and yeah, you even have the empty set, which is what you get when you decide to pick no elements at all. And here's where it gets kind of crazy. The number of subsequences grows exponentially. For an array with n elements, you have 2 to the power of n possibilities. That gets big, really, really fast. So how in the world do you write a program to generate all of them, systematically, without missing any? Well, the secret isn't some complex mathematical formula. It's actually a super simple but really powerful decision that we're going to make for every single element in the array. Okay, let's really dive into this, because this is the core idea. This is the whole game. All 8 of those subsequences that we just saw, they are all just the result of a series of these simple pick or don't pick choices, applied to one element at a time. Let's see it in action. How do we build the subsequence 3, 2? Simple. We look at the first element, 3, and we decide, pick. Then we move to the next element, 1. We decide, don't pick. Then we get to the last element, 2, and we say, pick. Boom. 3, 2. Every single subsequence is built just like this. You know, this simple pick or don't pick idea, where each choice leads to another set of choices, it just screams recursion, right? It's the perfect candidate. So let's translate this idea into the logic of a function that actually calls itself to explore every single one of these possibilities. Our recursive function is going to have 3 main parts. For each element it looks at, it's going to split reality into 2. There's the pick path, where we add the element to our list and move on. Then there's the don't pick path, where we just move on. And finally, and this is super important, we need a base case, a stop sign, that tells the function when we're done. But wait a minute, this brings up a really critical question. If our function decides to pick an element and it goes down that road, how does it ever go back in time to explore the other reality, the one where that element was never picked in the first place? The source material for this explainer gives us an absolutely brilliant analogy. Think of it like a trial room in a shopping mall. You pick a shirt, you try it on. That's you exploring the pick path. Now, if you want to try on the next shirt, what do you have to do? You have to take the first one off. You can't just keep piling them on. In our code, this concept is called backtracking. After you explore a pick decision, you have to unpick it to go back and try the other path. So what does this all actually look like when it runs? Well, we can visualize every single decision, every path our function takes, using something called a recursion tree. It makes it all make sense. So we start at the very top of the tree. We're looking at the first element, at index 0. Our current subsequence, let's call it our shopping bag, is completely empty. And now we face our very first choice for the element 3. And right away, the path splits in 2. The function makes 2 new calls to itself. In one call, we decide to pick 3, so our subsequence becomes 3. And we move on to index 1. In the other call, we decide not to pick 3, so the subsequence stays empty, and we still move on to index 1. So let's just follow that left branch for a second, the one where we already picked 3. Now we're at index 1, looking at the element 1. And guess what? We do the exact same thing again. We split. We make 2 new recursive calls, one where we pick 1, creating 3, 1, and another where we don't pick one, leaving us with just 3. And if we follow that path all the way down, we eventually add the 2, and then the function gets called for index 3. But wait, our array only goes up to index 2, so index 3 is our signal to stop. That's the base case. We've made a decision for every element, so we print our very first result, the full subsequence 312. Now here comes the magic, the backtracking part. After we print, that function call is done, it returns, and the very next thing we do is remove the 2 that we just added. We're back in the trial room, taking the shirt off. This resets our state back to 3-1, and that's what allows us to then explore the other choice for index 2, the don't pick path. This process guarantees the tree explores every single possibility. Okay, so let's zoom out for a second. What did we actually build here? Let's summarize this powerful pattern and take a quick look at its performance. All right, when we talk about time, this thing is exponential, which, makes sense. Our job is to generate all 2 to the power of n subsequences, so it's going to take a while. The extra n in there is because it might take some time to print each result. But the really great part is the space. The extra memory we need is only proportional to the size of the original array, just to handle how deep those recursive calls can go. So here's the crucial point why this really matters. This is not just some niche trick for finding subsequences. This pick-don't-pick idea is a fundamental, powerful template. Once it clicks for you, you can adapt it to solve a whole class of other problems. Think about finding combinations or subsets or anything where you have to generate all possibilities. It's a brand new tool for your problem-solving toolkit. And to wrap up, let's just think about the power of this pattern. You now have the blueprint to generate everything, every single possibility. So I'll leave you with a question. How would you change this logic? How could you add a simple condition so that instead of just printing everything, you only keep track of the best one according to some rule, like, say, finding the longest subsequence where all the numbers are in increasing order? That's the next level, and it shows you just how powerful this simple pattern truly is.